Hello everyone, welcome back to the Generative AI course, and we are into part 3 where we are going to take a deeper look into machine learning and deep learning, and we'll be going beyond to the hype to understand exactly how machine learning and deep learning works together. So the most complex AI system are built in one simple concept, that is, again, data goes in, algorithm compute something, and then predictions come out. So our goal is to train that algorithm to find the hidden rule in the data. So as we talked brief about that, machine learnings are divided into multiple paradigms, and supervised is one of them. And we are going to take a look on couple of models that is a part of supervised learning, where we are going to provide the data. We'll split the data into the training data and the test data. So this is where we act as the supervisor. We train the model using labeled data and give it a input X, and the correct answer Y is expected to be out. So the machine jobs is to figure out the mapping between them. So supervised learning, as we talked earlier, that supervised learning has two main goals. That is regression. That means predicting a continuous number, a value that can be anything within a range. And simple example could be predicting a value of a property or a house, and based on some different factors, or predicting the next week's temperature. Again, like it's a linear data. And the other thing is classification, there where we are predicting a predefined set of options. So think about like an email where you can predict that email as a spam or not spam, or let's say like the multiple pictures are given and we are identifying the object as bottle. So that is a problem of classification. So over here what I'm showing you right now is linear regression. That is one of the algorithm or the model for this supervised learning. So where the generate data is our problem statement, we have to predict the prices of the house, and the x is our input, and the y would be a prediction. So over here in the graph you can see there is a linear graph. The scalar graph is being constructed over here. The house sizes increases, the price increases. So this example we are going to take a look in a detailed demo. So as I said, like the machine algorithms models work on two special things: the trained data and the test data. So in specifically in linear regression is our fundamental model. It assumes the relation between your input and output as a straight line, as we saw in the previous graph, and the simplest way to predict a continuous number, as I told you, like predicting a house value. So over here we are splitting the part of that data, the labeled data, into the trained data and the test data. So 80%, which is again like industry thumb rule, like for training any machine learning model, we use 80% of data as training data, and remaining as 20% as testing data, so that we can evaluate our model. And for our demo, we are going to take a help of the toolkit that is sklearn, which is being considered as a Swiss Army knife for machine learning. We use it because it's built for simplicity and consistency. So consistency, as in like almost every model works in the same way. You import the algorithm, you create the model, and you do a model.fit to train that, and then you call model.predict to make a forecast, to make a prediction. So over here, let's actually just go back to our collab so that I can show you the demo for this linear regression model, and we'll be predicting some data, and we'll first of all train our model and then evaluate model with the test data, and then we are going to run a prediction, run a forecast so that we can forecast something. So I'll just go back to my collab. As in my previous video, I explained that we are going to use the collab for our all use cases or demos. So I will just open my notebook, which is specifically I built for this ML demo, and I'll show you like what we are talking about, the linear regression model or algorithm. So in my last video, I showed you like you can open any new collab notebook, like just creating a new book, and once that book is created, you can take help of Gemini to assist you in code, or you can, if you are well versed with Python, then you can start writing by your own. So we are importing some of the libraries over here. So NumPy is for doing any numeric operation, as I said, and this is for plotting the graph. So though like over here in the second part, we are plotting this linear graphs using this linear regression algorithm. So that's why we are using this library. It's not related to machine learning, but just to plot our graph. And this sklearn, which I was telling you, that is the core toolkit where we are importing the linear regression model from this toolkit, which is already built. And then we are selecting this train, we are importing this train test split. This is again a standard library to split the data into test and train data. So in part one, we are constructing a synthetic data so that we can do some random prediction going forward. So over here, you can see NumPy random seed. As in my last video in Python Basic, I told you like we use that random to generate the random operations to do some random operation mathematical operations. So over here we are constructing the input, which is 100 random numbers between 0 to 2. So we are considering that as a house sizes. And over here y, as y we are constructing a linear which is having a scalar relationship with the x, that is our square feet. And over here we are visualizing, so you can skip this part, I'll directly show you. But part 3, which is main, how you actually build any machine learning model or train any model. So over here you can see I have this x trained it, x test, and y train and y test. So both the 80% of test data we are splitting. And so over here we are using this linear regression algorithm. We are just initializing our model, and we say model fit. So model fit is a standard function where it takes this first argument as the train data and the second argument as y train. That so 20% which we kept aside is this one. So the model dot fit line is a magic moment where the machine trains it. It calculates the perfect line that minimizes the total error all the data points has. And in the part 5, we are evaluating how good our model is. So we are evaluating that based on the score. So this is the R squared score, and the R square scored, we are printing this R square score like how good our model is trained. So we can, based on this factor, this numbers which is being output as a score, we decide like our model is trained good or not. And if we keep going down, and over here we are making a prediction. So over here we are creating a new axe for the new house sizes, and we are passing that to model.predict. So again, it's a predefined function predict. We are passing the square feet sizes for the prediction. We are printing that. We are enumerating all our input, and over here till this part, I'll just minimize this. Till this part, we have this our model created, and it's predicting this input which is passing over here, and again plotting the graph for that input. And finally, so when we say like R score, when it is close to 1, that means like our model is trained really well. And anything nearer is also near to 1 is also good. Like if it's 0.1 or 0 point something lower than 5, I would say, then it's we need to do more tuning of this model. So let's run this part. Like as I said, like we'll be running this, and over here, so this is the initial plotting which we did for our this part where we visualize our raw data. And the second one is like after our trained model, and we are trying to predict the prediction for new house sizes which we passed as an input, and the prediction we are getting is related to this. And then again, after training our model, we printed this plot again, like visualize the learned data. So it actually shows this actual data versus learned model. The learned regression, this red is a regression line, and this blue dot is the actual data point. So over here it's perfectly constructing that into a linear data. So this is the simplest model of linear regression. But where it lacks, like when we have the more complex data, like it's not relational. For example, this house square feet size and the price prediction kind of linear. But when we have more complex data, then we have a different algorithms which to follow, that is gradient boost. So we can have a look on this gradient boost algorithm. So that's a again as part of supervised learning. So where we have more advanced, this is a more advanced technique, and data has complex patterns. So unlike the previous example where we were having a linear data, over here we have this sort of sign data where there is much more randomness in the data. So consider this gradient boost is kind of works in a team of expert where there are multiple decision trees sequentially which evaluates themselves, and then other decision trees makes reevaluate those guesses whatever the initial model or initial decision tree gave as an output. So consider that the next tree is kind of tutor like which actually focus on entirely on correcting the mistakes of first one, and this process repeats itself multiple times and leading a highly accurate combined prediction. So for this one, you can see a single hosting team of decision trees. We have this one decision tree created at a time, and then we define that as an estimators, like how many decision trees we want to have included into this gradient boosting algorithm. And to check the accuracy of this model, we use this RMSE, that is root mean squared error. And in this case, in the earlier case, the accuracy, like when we get the score near to 1 was considered as high, but this is a reverse one, like it's a root mean squared error. So the error is less, that means like our model is working perfectly fine. So If these are large number, that means like our model is not trained good. So let's again take a look on the code of this gradient boosting algorithm or model. We'll just go back and I will minimize this. So over here, I already added this gradient boost algorithm model example, where again like we are importing the required libraries, NumPy, matplotlib library for our graph plotting, and then we are importing this gradient boosting regressor from again the same toolkit sklearn. And over here we are importing this decision tree also. As I said, like we are having multiple decision trees, so one weak decision tree will be evaluated multiple times with the rest of the one, so that we can make a stronger combination as a team. So we are importing this decision tree as single, and then again in this case also we are going to get the data train and test split data, because we are going to split that into again 80 to 20% as we did last time. And in part one we are generating more complex synthetic data. So earlier it was we generated kind of linear with a normal expression, that's a sort of in a linear fashion. If property square feet increases, then the price would increase. So in this one we have this input and np dot sort, that's for sorting, and the random, like we are picking up random values as an x. So this was same for our linear regression, but the y is now we are having a sine wave with the noise. So over here mpsyn again like is from numpy library, and we are adding the randomness, and now this data is more scattered, the output is expected more scattered. And then again visualizing the data, you can ignore this, and now splitting the data again into the train and test part, x train, x test, y train, y test. Now creating this decision tree regression. So it's a single decision tree we are creating, doing a model fit, which is again the magic function for us, like x train and y train, passing the training data. Prediction, for predict we are passing the test data, and tree RMSE like is again root mean square error, which I told you like it's related to how much or the what the accuracy of the model. If it's less, that means like our model is less erroneous. If it's high, then it's a more inaccurate model. We are printing the RMSE of single decision tree, and then gradient booster boosting regression. So now we are doing like many weak decision trees combined to form a strong one. So over here NS estimator is saying add this sort of 100 decision trees so that we can get a strong prediction out of this algorithm. So later than we have this model boost model dot fit again doing the same thing, and boost predictions we are passing, we are evaluating with our test data and checking that our model is predicting our test data is correct or not over here, and then we are visualizing this actual versus this predicted data. So if I run this entire program in the output, so you see like in the raw data, we have this more non-relational data. So over here, with the single tree decision, you can see like it came as 0.2. That means a bit higher value, but the gradient boosting algorithm, which includes 100 sort of those decision trees, it came down to 0.1. That means this algorithm predicted more better, more accurate than a single decision tree. And the final one, which the plotting, which we are doing based on the trained model, is we are getting sort of this. So gradient boosting model is this purple line, and this actual data passed is this green dots, and single tree is predicting sort of inaccurate, though like not that much, but still inaccurate in comparison to our gradient boosting algorithm. So these two are related to this supervised regression algorithms, or to forecast something based on the previous past patterns or the input data. This screen is just showing the same thing. Focus on errors, combine the prediction of all the weak models, and then giving it a right the data, the output predictions. So now we just covered our regression algorithms for machine learning, and now again we will talk a bit about deep learning. Though like we covered a bit it at high level into a past video, but this time we are going to see a actual demo for this. What is deep learning algorithms? What is ANN, CNN, and RNN? The previous one where we saw this linear regression and the gradient boost algorithm, those are related to much of the structured data, like though like we were having input, but it was a sort of scalar input where we were having normal, I mean the simple input, and we are predicting the forecasted values based on the model performance. So deep learning, as we talked about earlier also, it doesn't deal with the normal structured data, it deals with the unstructured data where like images, videos, audios, and there like we need deep learning to do the complex forecasting or predictions or classification for us. So there comes this deep learning algorithms or the networks, neural networks. The neural network that we call that as in artificial neural networks, and which comprises of CNN and RNN. CNN is convolutional neural network, which is more focused on images, videos, and is majorly like used in computer vision. And the recurrent neural network is related to predicting the next word in the sequence. So it's related to text and sequence of speeches or writing the full line like based on the past information provided. So let's talk about the convolutional network. So the CNN is the ultimate image detective, I would say. It uses filters to break down an image and then learn about the features and building complexity from simple edges to the full object. So over here you can see I have these images and which can be just consider that like it can be laid as an pixel diagram. So we have this 28 by 28 pixel where every all the corners and the edges of this object would be a dark or gray color. So the density of the pixel. So in the convolutional model, what we do is we create a con 2D layer that actually slides across the image, and convolving is actually with the pixels to detect the basic features like edges or the curves for that image. So the output of this con 2 layer is 32 features map. And in this entire this CNN model, then that is passed to this max pooling 2D. And this is a downsizer. It actually reduces the image size from example this 26 by 26 to 13 by 13, keeping only the strongest feature signals. So it learns zero parameters. That means like it removes the unnecessary information, just compresses that into the information that is important to us. And then it can be passed to one more con 2D layer, and that 2D layers can be like of different filters. So if we say like con 2D layer with a 64 filter, that would be placed in between of it. And this layer uses 64 filters to learn more complex like features by combining simple edges found earlier. So for the simplicity, I'm not showing this con 2 layer again, but just passing the output of my compressed image to flatten layer. So flatten layer is this layer takes the 3D feature cube and unrolls that into single long list of numbers. So all this right now we are having this 28 by 28 pixels and that is compressed. Then flatten layer would be having this series of numbers because we are going to predict on the numbers ultimately. And the final layer, which is a dense layer, so this final layer outputs the probabilities. So based on this image, which is the input image of t-shirt, let's say it we do that con 2 layer on that 28 by 28 pixel, then doing this max sizing, max pooling, which consider the only important pixels. So over here, so this is important pixel, that's and then flatten those pixels into numbers, and then we do a prediction on that part, the weather. So it matches to the probability of a sneaker. If it's a shoe, then the probability would be 92% of that output. And one more important thing, when this model is untrained, its prediction would be a very random numbers. Like it could be 7%, 10%. With the, for example, predicting a shirt as shoe, 7%, 10%. But we do more epochs. That means like cycling of more refining predictions or training cycles. Then it will do the probability of any prediction would increase. So we can see that into the actual practice, so that the more network cycles we through like all these data, then call that as epochs. And in every cycle we continuously adjust these internal weights so that we can make our model more accurate to identify an image. So this one we can take example into our collab again. So I will open my demo sheet. So I am just opening my Jupyter notebook that is for right now is for CNN. So as we talked about, like this deep learning is built on neural networks, and we have these two key libraries, Python libraries over here. This TensorFlow and Keras. So TensorFlow is the powerful engine, I would say, and it's a framework like it handles all the low-level mathematical operations using tensors and ensures the training can scale across GPUs. So consider, I mean, need not to go into much depth, but consider that as an engine which will do all the model training and prediction later. And the Keras is the easiest dashboard, I would say. Like it provides a simple high level building blocks commands, the commands which we are seeing over here, con 2D, max pooling and flattening and densing, that abstract away the TensorFlow's complexity. So use Keras to quickly define and train powerful models. And again, this NumPy you are already aware, and Metaplot where to plot the data. So in first part, we are going to import that, prepare the data. So for preparing the data, we are actually like taking the existing data set via Keras. Keras, like we have this fashion minist data, which will load the data related to fashion, all the images related to fashion, t-shirts, glasses, shoes, and all that. We are again creating train images, train labels, train test images, and test labels. And over here, the train images as of type float 32, normalizing the pixel values from 0 to 1, as these are gray images, like not called colored one. And then later we are defining the classes of our data, so that we can classify or predict like which image belongs to which class. So we are going to predict the output from these classes. And now we are defining our model. So over here we are creating this model instance, and that is with sequential con 2D, as we talked about it. That con 2D, this layer uses 32 filters that slide across the image and convolving the pixel to detect basic features like edges, the curves. The input image is 28 by 28 cross 1 for grayscale, and we are creating these 32 filters. And max pooling, and this is this downsizing, and then again adding up one more con 2D layer that is with 64 filters, and then flattening the layer, that is to unlong the list of numbers. And then we do this dense. So dense is the final layer which outputs this 10 probabilities of this clothing item. And the activation function is we are using is softmax. Then we compile our model. Once the model is compiled, then starting model, and we start with the 5 epochs. So over here you can see I have this model CNN which we compiled the previous one, and dot fit is again that function, provide the input, the training input, and then we decide this epochs. So epochs like number of processing or the neural processing it should do, and then we will say like okay, training of our model is complete. So till this part we have just trained our this model, and in the next part we are doing a actual prediction of one past input image. So over here, so with the image index, actually we are just using this image, and out of our this the data set which we loaded, and we are passing that as input to predict to our model dot predict, so that we can predict that image and find the highest probability of that image. So I will just run this entire code, and this will train our model. So it may take time because it's 60,000 images it's training on. And I will actually recommend you to just go to your runtime, and in this runtime change the runtime to T4 GPU instead of CPU if CPU is there for you, so that you can have more power, more processing power. So you can see like epoch 1 is running over here. So it's doing one processing cycle, then epoch 2, and in every epoch it says that accuracy and loss. So you can wait like till all the epochs are done, and then the past images of t-shirt, and let's see like if it's predicting that correct or not, the our trained model. Okay, so the input which being predicted is of shirt, and over here as we printed this probabilities of 10 classes, you can see t-shirt, shirt 0%, trouser 0%, coat 3%, shirt is 96%. So our model, that means our model's accuracy is quite good, and we are predicting our provided input image with a confidence. So this solves this part of a classification problem where like it classify or is finalize the category of the input image. So you can do that on any data set where like it in real time it uses for the object detection or classification problems. You can use this CNN. So again, like this CNN is part of deep learning neural net, which is not a part of generative transformers, but yes, it used to be like this. It's a part of deep learning, and we'll get to that generative transformers like how these are better. But we should have a minimal foundation layer or layer of machine learning and deep learning to proceed to get into those discussions. So we should be knowing like why these transformers are more advanced than these CNN and RNNs which are there in deep learning. So let's get back to our slide, and we'll just proceed with one more neural network, that is RNN. And as the convolutional neural network was working with this image detection, these RNNs are meant to do the word predictions. So over here we have this neural network where like we are predicting the next word in the sequence. So it uses this LSTM, that is long short term memory, like to see what was being there in the history and then predicting a word in the next. So I will just get to the demo directly, demo of this. so that it's simple, it's simpler than CNNs. So again, we are importing this TensorFlow and again the keras. And over here, we are importing one additional, that is tokenizer, so that we can tokenize our input and then pass on to the further processing. So prepare the sequential data. So I'm just preparing that as text. Tokenizer, tokenizing that data, splitting that data into words and then words into the numerical denotations. So this tokenizer assigns a unique ID to every word, and then we prepare our data into parts, the input word X and the target word Y. Over here you can see. And then reshaping that data into 2D array with sequence of length 1. So it's actually normalizing the data into numbers only. And over here, define the RNN and LSTM model. And we are just defining our model sequential function and then embedding. Embedding is nothing but is the word encoder. It takes the simple word IDs and convert that into 10-dimensional array. So it allows the model to understand the meaning of the word. So for example, making fox dog into a numerical similar fashion. So when we say LSTM 50, that means like the 50 interval units process the word one by one. So this uses the internal gates to decide what context should be remembered. So this is how it maintains the context over a full sentence so that it can predict the next word in the sequence. Now we are compiling our this RNN model. This defines the rule of the game, like before processing or before running the model. So the optimize the ADAM, that is the strategy or the algorithm, and it's actually adaptive movement estimation algorithm, most popular and effective optimizer. And the loss function is a single number of quantifiers how bad the model is prediction was compared to the actual correct. And this metrics is a report card. Metrics are used to monitor and report the performance of the model. So unlike the loss function, which algorithm uses internally to adjust weights and metrics are chosen, so this metric, the report, the accuracy metric is the most common metric. So it simply tells you the percentage of times the model makes a correct prediction. So once we compile it, again, like we'll do the same model dot fit. So train for a few epochs, like you can set these epochs as processing iterations. And once you, if you do it more, like it's always better. But for the sake of like it's we are running that into our collab TPU, so we can just keep it small also. But we would not get that much of accuracy if we keep that small. So once you do that, the finally we can just run our model. We can with a dot summary, and then we can just evaluate. We can pass the input and evaluate our model. And later on, like you can, once model is evaluated, you can pass the input to predict to make any future prediction. So if I run this, so it will start training the our RNN model. So over here it says like RNN training complete, and it displays this output embedding 1 to 10 LSTM which we defined, and the total parameters like it trained on, and trainable parameters and non-trainable parameters are 0, and the model loss is 1.7 and the model accuracy is 87%. So it's a pretty decent model which we built for this model prediction. And when we want to predict the next word, so over here, so we created one this daf. As I told you, like in the Python basic, that daf is defining a function. So we are creating one function that is model, that is predict next word. We will pass the model and the tokenizer and start word. And over here, once this def is built up, then we are doing this calling of our this predict next word function. We'll do this predict next word, and model we are passing that model which we just compiled, and we are passing the tokenizer to tokenize the sequence of words in the numerical fashion, and then we pass the input word. So when we say like quick, so it predicts this fox, and when we say jumps, then it will predict the next word in the sequence that is over. If I run this prediction and if I go to the output, then we see like our input was quick and the predict is brown because it's a brown fox, and then input is jumps, then it predict over. So that's how we build our this RNN to predict any word in the sequence, and it uses the LSTM for making the short term memory, like where, as we say, like intervals of 50 would be maintained for our this scenario. You can keep it a bit more, but again, if we want to predict or write something long, then these RNN models are challenging. So that's where like we have a new deep learnings models and architecture that are called as generative pre-trained transformers, that we in short we say like GPTs. So now, because we have our context of machine learning and deep learning, and now we can get into the next learning part that is related to the transformer. So as I said, like this deep learning RNN CNN is powerful, but it has limits. So for true human quality AI, the field has moved to the transformer models. So why shift from RNN and CNNs? Because unlike we don't have capability of doing parallel processing, like parallelism, unlike RNN, which processes the sequences only one by one, and with the LSTM also, like it has a limited memory. What if like we want to write some huge paragraph and we don't have that memory? So that's where like generative the pre-trained transforms come into picture. And these RNN and CNNs are the foundational for the large language models like GPT and Gemini. So in our next session, we will deep dive into the transformers models, especially encoders decoders architecture, and how they achieve the incredible performance. We'll also take a look, and then we will talk about a bit of demos of transformers from there. So stay tuned for the next session. Thank you.